Welcome back, everybody. Did we? I, okay, let's get going. All right, checking stuff out. Yesterday, come on. Just kidding. All right, yesterday we were talking about translations. Today, I feel like I had this conversation with you guys, and we might have a little bit. We're continuing on. We're still in 3.2, just so everybody's aware. Our first whole topic was just about translations. Today, we're going to define for ourselves and start looking at what we call compositions. And I'm going to call this composition or compositions of rigid motions. Okay. First and foremost, what's a composition? Like if I said, what is something composed of? How would you answer that question? Like, what am I composed of? I'm made of cells, because you're just giving me the parts, right? Now, you could be more or less specific, right? I am composed of bone, blood, and muscle, and that's essentially it. You could be way more specific. I'm composed of protons, electrons, atoms, and all that stuff. Did we talk about compositions yesterday?
Yes.
Did we have that written already?
Yes.
Why don't I have it written on mine?
Oh, we did.
We did?
See, I felt like I was having deja vu.
You know, I just wrote it like directly below it, so I don't
Oh,
know if you're not even reading.
yeah, because I wrote it right here. Okay. And I'll tell you, the vivid deja vu that I felt like I was having was because I was pretty sure that yesterday, and I'm pretty sure I'm right, but I've been wrong once or twice in my life. I think yesterday, very vividly, Lily said yes to when I asked about this.
Yeah.
Okay, so that was not deja vu, that really happened. Okay, cool. Well, we're way sooner, or we're going to way faster to homework. Okay, so looking at these. We started looking at them yesterday. The bell ringer still aligns with this, just for the record. Like, didn't change anything. We did on our bell ringer today multiple transformations in order. Now, I've already disappeared the bell ringer, but if you want a reference, and you guys have it, but Andrew and Camille, the bell ringer today, you don't have to do it, but on a sheet of graph paper, we reflected over 2 lines. So I'm only going to do it with a segment this time. But if we reflected this over this line, it would wind up here. That looked roughly okay to you guys? And then if I reflected this now, the dark red one, I'll change color, over the blue line here, I would wind up with this segment. Now, did we do a composition of transformations already? I did multiple transformations in order. And on your bell ringer, if you guys still have it out, was this L and M?
Yes.
Okay, which one happened first? L. So if we wanted to write what we did on the bell ringer, and this is going to be just, I'm just going to say find rule, because I think this is probably the last thing you have, example, find something. So this one's going to be weird for those of you that weren't in class, but the rule from the bell ringer, because it's this picture. On this picture, your guys' was triangle ABC, right? I'm going to do segment AB, and your stuff is going to match essentially the same, but you're going to have an extra point. Everybody okay with that?
Yes.
Okay, so here's, gosh dang it. B double B prime and A prime, and A double prime and B double prime. When we did this, what all I want us to do is let's write the rule for this picture, or for your picture on the bell ringer. Now, if we're looking at this, what happened first? Did we reflect over L or reflect over M? L first. So when I start writing this, I'm going to have a reflection composed with a reflection, right? There's 2 different reflections. And then your guys's will look like triangle ABC. Mine is just going to be segment AB. This is what we are, literally, like the object that we're reflecting. Now, you guys were able to tell me that we did L first. I'm cool with that. I can tell that there's a reflection and then another reflection composed with it. Which one gets L and which one gets M here?
The one closest gets it.
The one closest, because it happened first, gets L. So we should have an L here. And what should this one be then? M. Now, this is purely to get the notation out. This is weird that it does it this way. When you see this again in Algebra 2, we will use the terms inside and outside. And if that doesn't mean anything to you, you don't have to write this. But this is what compositions look like in algebra, which kind of sucks, to be honest. The pretty standard first step is rewriting these instead as f of g of x. And when we write it in this form, do you agree that there is a very clear inside and outside? Like, we could write these in this form as well. G is the inside here, right? And notice it's the exact same. If I did the composition of M composed with the composition of L of some, I'm just going to say triangle, just for simplicity's sake, this would be reflect M after you've reflected L. Like, it's the same thing, and I can see that L happens first. It's the inside or the closest. Okay, a little bit of algebra stuff. It's there, we're not using it directly. Okay, now we're going to expand on this, and I'm just going to use this picture for now. When we erased these lines, and I'm going to erase them again, and if I said, hey, what happened here? There's no reason that anybody would ever think, especially if I changed the notation to not be double prime, there's no reason that somebody would ever look at this and think, well, of course he reflected twice. Because again, you guys all simply see a what? We all agree that if we skip that middle part, it just looks like it translated this far. Now, it turns out they are the same thing, right? Like, I can see that it's the same thing. There is a translation that does the exact same movement. Now, we get our first theorem of the chapter with that idea, not a new section. We're going to call this theorem 3.1. And it doesn't formally have a name. I'm going to give it a name, composing or composition of two reflections. Now, on the bell ringer or on the picture that we had up above, there was something special about the lines L and M that we reflected over. Now, not special about where they were located necessarily, but is there, if you look back at your bell ringer, or I'll draw the picture again roughly. When I drew my two lines, I had you guys use graph paper. Did anybody's come out like this? When you look at the two lines you drew to reflect over, nobody did that, right? You guys probably all followed the lines and meant that you had what sort of lines? They were parallel. Now, I'm going to give you guys the option here. Some of you guys prefer wordy stuff over just picture, and some of you prefer picture over words. On this one, we can do both, but I think the wordy version is kind of ugly. I'll write it if you want, but let me just try to word it first. We're going to draw the picture, and then we'll decide on the wordy version, okay? So check this out. Really quick and easy picture. I'm just going to do that same segment picture. It doesn't have to be perfect, but we're going to have parallel lines. And I think it's easiest if we just do a single segment. So it doesn't have to be crazy. I'll give you guys a second. Let's say we reflected this. And I'm only going to name one of these points. I'm just going to draw all of them. Gross. I should move that other line. This is like the same idea that we've seen now 3 times, right? L and M. All right. Let's say that this point's name is Z, which means I'm going to pretend that we didn't do this one for now. We'll call this Z. I guess we'll just call it double prime. I'm fine with that. Okay. When we look at this theorem, the picture that we all worked out, and you've all seen the theorem at work. If this distance is D, so if, and I'm going to have to name this ZY. If ZY reflects over L and M with line L parallel to M, then we see, what did you guys say it looks like if we, like, I only show the middle part just so I can see it, but if I just go from here to here, what does it look like? A translation. Now, that is the first little part of it. There's a lot more words if we want to be really clearly. This is about where I would stop here. There's a specific length though. The real wording to this theorem is that if you give me something and reflect it over 2 parallel lines, which is essentially the same, then we see a translation that moves twice the distance between the lines that are parallel. Now, that's what we saw. The wording is kind of ugly. If this distance is 5, What's this distance? 10. Now, when we look at this, I don't want to have to do all that wordy stuff. We see a translation, and I'm just going to say by 2d units. And the way that I'm going to make this make sense is if this whole distance from y to y prime is 2d, then what's this distance? So careful. It's like a translation. This is my 2d right here. It's just a single d because the distance between this and this is twice this distance. Okay, now looking at this, here's the whole theorem. I've made it a lot shorter than I made it for fifth hour yesterday. Do we need more words to make sense of this picture? Like, if you want it, I'm not going to require everybody, but just an alternative with this specific picture. If we wanted a EG or IE, if you will, of this exact situation, this is all that I know. If distance from L to M equals D, then the length of the segment, and it doesn't matter whether we use y prime or z prime, doesn't matter. I'm going to say z double prime in this situation based on the picture equals 2d. That's the same theorem. That's it. Now, the most important part of this theorem, and the only way it works, is what do we have to know is true about these? They have to be parallel. Okay, that probably could have been covered yesterday in class. Don't know if we ran out of time, if we had a time killer of some sort. Did we have a time killer? I don't know. I call it a time killer. I don't know that I necessarily agree with that word. We do some random stuff in here, right?
No, we did like
Even when we kill time, maybe not every time, but most of the time, if I go on a tangent on something, are you still learning something?
yes.
I hope most of the time that's true. Sometimes maybe not, but deal. Okay, I'm not going to leave Andrew and Camille completely behind. Here's the deal that I'll make with you. I have an assignment for you, and the problems seem as though they're arbitrarily chosen. They are very much not just randomly picked, just so you know. It's not going to be this through this like normal. Instead, it's a collection of like 10 problems, so it's not crazy long. It looks crazy long only because it's not just 25 through something, whatever. Okay, starting now, and I legitimately think we'll come close to finishing, if not completely finished. I don't think it'll take 35 minutes. I want us to work on 3.2 for the time being. I'm not going to stop the video because if everybody finishes in 15 or 20 minutes and it's going well, that's awesome. But it just means that we can get a head start on tomorrow's stuff so that that'll keep perpetuating. It won't always happen, but if we get a head start on 3.3 today in class, then we'll have time for 3.3 homework tomorrow. Cool. I'm going to pause the video. If you don't hear me talk anymore, it means that the homework took longer than I anticipated. But I do want to remind you, smash that like button, subscribe, don't ring the bell, visit my Patreon. Cool.